is going to tell us about adiabatic deformations of quantum droplets.
Okay, thanks. Thanks, Michael, for the introduction, and good morning, everyone. Before I begin, I would like to thank the organizers for inviting me to the conference. It's a pleasure to be here, and I hope you will enjoy my presentation. So, as announced, I'm going to talk about certain time-dependent deformations of quantum droplets. This is based on these two papers, the first of which was written with Benoît Estienne, and the second one again with Benoît, together with Bastien Lapierre, Per Moussavi, and Jean-Marie Stéphane. Most of these people are actually here today in the room. So there are two things I should note about this talk before I begin. First, note that the talk that follows mine by Per Moussavi will talk about a very similar subject, although we made sure that there's no actual overlap in terms of content. And also, well, thematically, what I'm going to discuss is very close to several of the subjects in this conference, especially some of the motivations of the talk of Andrea Capelli, which will be, I think, on Thursday. And the second note, I should actually mention that I've given a very similar talk in Lyon and Grenoble recently, so some of you have actually seen a very similar talk, so I apologize. Okay, so let me begin first by introducing the subject, and in particular giving a very broad motivation to explain where this research comes from. In the broadest sense, the motivation comes from the fact that in physics, diffeomorphisms, i.e. Continuous deformations of various continuous media, smooth deformations, diffeomorphisms are ubiquitous. If you're interested in gravitation, you know that diffeomorphisms provide the gauge symmetry of general relativity. If you're interested in hydrodynamics, you may think of fluid flows as time-dependent diffeomorphisms. And finally, in condensed matter physics, you're of course allowed to deform your sample at will, but this is especially powerful in the context of topological phases, which admit an emergent gauge redundancy under material diffeomorphisms. And so, the broad, whatever sort of physics question at some point you're going to have to consider certain observables associated with diffeomorphisms. What kind of, for example, linear response I could have to certain, for example, time-dependent deformation. Ask this in any of these fields. Today I'm going to focus on the condensed matter side of the story, so I'm going to focus in particular on the general problem, which is to prove the emergence of these gauge invariants under diffeomorphisms in topological phases of matter. Now, I should mention at the outset that this is an immensely broad and actually pretty ambitious question, so I'm not going to address it today. But it will be the broad motivation that I'm going to use, and we will indeed see some hints of the answer to this question in what I'm going to discuss. Specifically, I'm going to focus throughout on what I'm going to call quantum droplets. So these droplets, as you've already heard in these talks, are literally two-dimensional droplets of electrons in a conductor placed in a very strong perpendicular magnetic field, and they're confined in this region by some weak confining potential. Now, in that context, the key role of smooth deformations, diffeomorphisms, has been recognized for decades. Indeed, these droplets are effectively incompressible quantum fluids, so they have a symmetry and area-preserving deformations. And in particular, if you look at their linear response to time-dependent deformations, this response includes one coefficient, which is quantized. I shouldn't touch the blackboard. One coefficient, which is called Hall viscosity. And so, at this point, by the way, if you don't know what Hall viscosity is, don't worry. I'll talk about it a bit later, but it's not crucial. The thing is, my talk will actually be along the lines of the initial derivation of Hall viscosity by Hazel and collaborators. Indeed, what I'm going to consider are certain time-dependent deformations of a droplet. So you should imagine having a droplet like this one, which you very slowly deform and eventually return to its initial shape. And the idea is that as you do this, the wave function of your droplet is going to accumulate a phase, a Berry phase, and my goal is going to be to compute that Berry phase and use it as a probe of certain properties of the droplet. You have a question already?
Yes, so the deformations are done by applying external forces?
That will be part of the talk. I'll explain what I mean by applying these deformations. I'll show the Hamiltonian.
Okay.
So I want to apply some deformations and in particular make sense of the word deformation, so that will be part of the talk. And in doing so, we're going to find several results, which I want to anticipate already. The first is that we're actually going to find back Hall viscosity, but we're going to find it in a fairly generalized way, in the sense that first, we're not going to find it on the torus, but on a plane. And secondly, we're going to find it in an infinite dimensional parameter space, whereas it's normally defined in a two-dimensional parameter space. Furthermore, and perhaps more importantly, we're going to focus on certain deformations that affect the edge of the droplet, which here is highlighted in red. And so you will see that by applying these deformations, we're going to probe the properties of the edge, and in particular, we will see hints of the fact that there's a distinction between bulk and boundary behavior. In fact, we will not quite see the kind of statement that I'm writing here, but again, there will be hints of the fact that deformations in the bulk are a gauge redundancy, whereas deformations on the edge are an actual global symmetry of the problem. And so all those are things that we're going to see. So with this motivation in mind, here's now the plan. I'm actually going to begin by reminding you what Berry phases are, and I'll show them in a particular one-dimensional toy model, just to explain how they work. Then I'm going to move to the two-dimensional world, and I'm going to consider two kinds of deformations. First, I'll consider unitary deformations that affect both the kinetic term and the potential in the Hamiltonian. And then I'm going to turn to very different deformations of the potential alone. And as you can see here, these are the kinds of deformations based on the two papers that I mentioned on the title page. And so that's it. And indeed, if you have questions, feel free to ask. That's the point of the talk. Okay, so let me begin here with Berry phases. What I'm going to do first is just to remind you very broadly what Berry phases are, so we're all on the same page. Then I will show how, in a simple one-dimensional quantum mechanical system, you can actually find Berry phases from adiabatic deformations. And then I will briefly mention what happens in a conformal field theory, where diffeomorphisms acquire a central charge, and this central charge actually affects the Berry phases that you find. So to introduce Berry phases, suppose that you have a quantum mechanical system whose Hamiltonian depends on a certain set of continuous external parameters. Here, I'm denoting these parameters collectively by the letter G, because I eventually wanted to think of them as labeling a point in a group manifold. But for now, you should just think of this as a convenient shorthand notation for all the continuous parameters. And so, because the Hamiltonian is parameter dependent, so is its spectrum. Here I'm going to focus on one particular family of eigenstates, and I'm going to assume that the corresponding energy is isolated and non-degenerate everywhere. The question we're going to ask is the following. Suppose you are an experimenter, you look at the system, and you decide to change the values of parameters in time, in a time-dependent manner. So your system is now following a path, gt, where t is time, in parameter space. And the question is, can you solve the resulting Schrödinger equation? If you assume that you actually carry out this variation of parameters very slowly, and provided you do it cyclically, so that you start from some point in parameter space and eventually return to it, as you do this, in fact, the final wave function is going to coincide with the initial one up to an overall phase factor. That's inferred by the adiabatic theorem. And in fact, the phase factor, as probably many of you know, the phase factor happens to be this phase here, which, as you see, contains the first term, which is this integral over energy, known as the dynamical phase, which we're going to completely disregard. And the second term is the term we're actually interested in. That's the Berry phase. Notice in particular that the Berry phase explicitly comes from the parameter dependence of these eigenstates of the Hamiltonian. Now, this is fairly general for essentially any kind of parameter dependence in quantum mechanics, but the question that I want to focus on is what would happen if you think of the configuration of a sample as a choice of parameters? What happens if you start deforming your sample in a time-dependent manner and think of these deformations as time-dependent parameter variations? And so to describe this, I'm going to focus here on the simplest kind of situation, so a one-dimensional quantum mechanical system, so that the wave function of the system, well, actually a single particle, the wave function is 2 pi periodic. And what I want to do is act on that wave function with certain circle diffeomorphisms. Abstractly, those diffeomorphisms are functions, g of phi, that satisfy certain properties, but to develop some intuition, it actually helps to show you a picture. So here's a circle where I have distributed uniformly a bunch of points, and what I'm going to do now is to act on that circle with a sequence of deformations. And you see that here I'm mapping the circle itself smoothly while pinching it here on the right and expanding points here on the left. So this is one typical diffeomorphism you might consider. More generally, any smooth invertible map from the circle to itself is acceptable. Yes, indeed. So, those are diffeomorphisms. And what I want to do is to define a unitary action of diffeomorphisms on wave functions. So for every dphi of G, I want to define a unitary operator U of G acting on psi. And to define this, I actually have to tell you what's the value of this wave function at some point. So it turns out that a natural solution is this one. We can verify that thanks to this square root term here, this is indeed unitary. That translates the fact that the square of a wave function is a probability density. And notice also the change of argument here on the right-hand side, which really translates the fact that if you have a wave function that's peaked somewhere on the circle and you apply a rotation, well, your wave function had better follow the rotation. So that's what this argument does here. By the way, you will see that inverse diffeomorphisms are going to appear quite often in unfollows, just for technical reasons. So I'm going to lighten the notation, and instead of writing them as G to the -1, I just write them as G bar. Okay, so now we actually have a parameter dependence, if you will, which is labeled by these group elements G. And what I'm going to do is to assume that I can somehow choose a time-dependent family of these these diffeomorphisms, so GT of phi, and I'm going to act with those on some eigenstate of some Hamiltonian. For simplicity, I will assume that the eigenstate is actually a plane wave with some angular momentum J, and so the question is, what's the Berry phase that results from these variations? Well, the answer is just given by the general Berry phase formula I gave earlier, applied in this case to the case where parameter dependence comes from this unitary operator. And if you now use the unitary operator I wrote here, you plug it back here, use the fact that the scalar product of wave functions is an integral over the circle, what you end up finding is this very simple formula for the Berry phase. Two comments about this. First, notice that the Berry phase depends parametrically on the angular momentum of the wave function. And secondly, notice that even though parameter space here is infinite dimensional, the parameters are essentially all possible diffeomorphisms, the Berry phase is actually a fairly explicit functional of this set of deformations. It's an integral over space-time of the time derivative of G divided by the spatial derivative. I should also mention, by the way, that even though this is a one-dimensional Berry phase, I would like you, if possible, to keep it in mind, because even when we move on to the two-dimensional realm, we will, in fact, recover precisely those kinds of Berry phases on the edge of the system. Now, notice that so far, I've only talked about these Berry phases in the context of a one-dimensional quantum mechanical system. Obviously, you could do this in a one-dimensional quantum field theory, except that you would have to replace this spin by the many-body current. And in particular, you might want to apply this to a one-dimensional conformal field theory. And in that case, the subtlety is that the action of diffeomorphisms is no longer, well, it actually becomes projective with a non-zero central charge. And this central charge turns out to contribute an extra term in the Berry phase. Yes, Sasha?
Before even going to that to apply adiabatic theorem, you have to have gap
yes.
in a system. So,
yes.
Which in quantum mechanics it was clear that you can invent some Hamiltonian with a gap. But what about conformal field theory?
So actually, there's a theorem by Avron. It's actually a paper called the Adiabatic theorem without a gap condition, which tells you that the Adiabatic theorem applies even in the absence of a gap, provided you are located, the state you're considering is located on the edge of one of the energy bands. I think it has to be the lower edge probably, but so if you're applying this to a ground state, for example, this would apply. The only difference is that when you have a gap, you exactly know the time scale that you need to satisfy for the adiabatic theorem to hold. If there's no gap, you don't know the time scale, but it's still true the adiabatic theorem holds. So it's sort of system-specific how you're going to find the adiabatic constraint. But it's a very important point, especially because when I talk about droplets later, I will actually, well, we talked about this yesterday. They actually become gapless in the thermodynamic limit, and so it's important to apply the adiabatic theorem without a gap. Yes?
Can I think of GT phi as being generated by a velocity field that will flow from time 0 to time 2?
Very good.
Because then we sort of know what to do.
Well, yeah, but that's an extremely restrictive situation.
Right?
You can have that, but in general it need not be. You see, when you talk about the flow, what you're saying is the corresponding velocity vector field is constant in time. And then, sure, if you're okay with time-dependent velocity vector fields, then it's fine. No, sure. And in fact, you will see the flow appearing in 2D.
Because then we sort of know what to do, right?
Yes, exactly. Exactly. Mm-hmm. Okay, so in a one-dimensional conformal field theory, if you compute the Berry phase, you will actually have an extra term. And I'm skipping the computation here, but the extra term that you find roughly has the form written here, where you see the central charge C appearing. You don't need to know the details of these formulas for later. For those of you who know the Virasoro algebra, you may actually know that the third derivative that appears here is a remnant of the term m cubed in Virasoro, but this is not important. The only point is that there is, in fact, a noticeable extra contribution due to the central charge. Now, in view of these one-dimensional results, and if you think in quantum Hall terms, there's a number of natural questions that come to mind. The first question is, what would be the analog of these deformational periphases for two-dimensional electron droplets? And the second question is, given that here we have a contribution from the central charge, can we somehow apply adiabatic deformations to quantum Hall droplets in such a way that we eventually probe the central charge of edge modes? And so those two motivations are going to guide me in the remainder of this talk. So let me begin. So I'm now moving on to the two-dimensional world, and I'm going to consider the first family of deformations that I mentioned earlier, which happen to be called quantumorphisms, as I will explain. So to explain those, I'm first going to introduce, in general terms, what I'm going to call area-preserving diffeomorphisms. Then I will argue that quantizing those diffeomorphisms gives rise to what's called quantumorphisms. And then I'm going to use adiabatic quantumorphisms to compute certain periphases, and I will highlight the properties of these periphases. So to introduce area-preserving diffeomorphisms, consider just the plane, R2, where you have some vector potential A, and consider the corresponding magnetic field, which I write like this. Notice that here I'm using the language of differential forms because it's more convenient. If you're more comfortable with curls of vector fields, that's fine as well. This is the same thing. Now, by definition, I will say that a diffeomorphism of the plane, so a smooth invertible map, preserves area if and only if it preserves a magnetic field. By the way, for simplicity, I will actually assume that my magnetic field is uniform, but this is not a necessary assumption. You could actually go through the same computation even with a varying magnetic field as long as it's always non-zero. Now, in principle, this is a fairly abstract definition, so I immediately want to give you a few examples that I'm actually going to use repeatedly in what follows. So suppose that you label your points in the plane by polar coordinates. You have a radius r and an angle phi. And ask yourself, how could I map this point on a point where I'm going to deform my angle phi in an arbitrary manner while actually preserving the two-dimensional area? And you can easily convince yourself that if you do this, so if you locally rescale the radial coordinate by this derivative of the diffeomorphism, this indeed preserves the area form. Now, I'm going to focus a lot on these diffeomorphisms, so I'll give them a name. I'm going to call them edge diffeomorphisms or edge deformations. And you will see in Per Musavi's talk that he's actually going to use these quite a lot. Again, pictures are often more helpful than formula, so here's a picture. I've distributed a bunch of points in a disk in the plane, and what I'm going to do on that is really apply certain edge deformations. So here's one example where, as you can see again, I'm pinching the circle here on the right, so I'm increasing the angular density, but I'm decreasing the radial density so that the local density remains invariant. And the opposite occurs on the left here, where I'm increasing the radial density while decreasing the angular one.
Sorry, I'm a bit confused by, how is it this transformation at zero at the origin, right? It is singular.
It's smooth. It's smooth everywhere.
Is it? But how is it when I approach the origin?
Well, you don't quite see it here because of the way I drew the points, but it is actually smooth. You can verify. So
it's area preserving, smooth.
No, but area preserving and smooth, right, is not the
same. Same thing.
So actually, when I start, my quote the quantum Hall started with this project, and the initial ansatz they considered were, so when you ask for this constraint, you want to map phi on g of phi, and you solve the equation that tells you that this has to be area preserving. There's actually an integration constant here in the radial thing, and that integration constant tells you what's the circle that you leave fixed. As long as that circle has non-zero radius, the map is singular. It's not a diffeomorphism. But if you choose the circle to be the origin, then actually it becomes perfectly smooth. So that's what you find. And I had problems with this initially because it was not smooth, and then actually this happens to be smooth. Thanks. Okay, and so by the way, again, you can do pretty much anything you like as long as it's smooth. So here is a more interesting example where I'm pinching the circle at 3 different points and creating this sort of star-shaped droplet. By the way, you may notice from these pictures that these deformations manifestly change the shape of the edge of a droplet. So that's why I'm calling them edge deformations. These are the leading sort of finite deformations you can find on the edge of a thermodynamically large droplet. So this is why I'm focusing on these ones. And furthermore, I should already mention for future reference, these deformations actually include all area-preserving linear maps of the plane. So if you have, you work in Cartesian coordinates, you map xy on a matrix times xy, and the determinant of the matrix is 1, so it preserves area. That's actually a deformation of this kind. Okay, so this is purely classical so far. Yes, and now I want to move to the quantum theory. So suppose that you have some square integrable wave function in the plane, and you want to act on it with unitarily implemented area-preserving quantum morphisms. Well, I haven't said the word. Unitarily implemented area-preserving diffeomorphisms. So what would you do? Again, for every diffeo of G, you want to define a unitary operator U of G that acts on psi. And the starting point is exactly like in 1D. You would start by saying, well, for sure I have to change the argument of my wave function, because if my wave function is a Gaussian here, I carry out a translation, the Gaussian has to follow the translation, that's for sure. And furthermore, notice that because G is area preserving, there's no Jacobian factor on the right-hand side. But you can also see that I've left a huge gap here, and there's a good reason for this. That's because ultimately we want to do this with charged wave functions, charged states. And those states are coupled to the vector potential. And we want to compute Berry phases, which you would compute, for example, by imagining some interference experiment. So it is crucial that whatever you do preserves your gauge choice. The gauge choice doesn't matter, but once you've made the choice, it had better preserve it. And so to do this, and keep in mind that area-preserving diffeomorphisms by definition preserve the magnetic field, but this does not imply that they preserve the vector potential. In general, the vector potential does change.
But why couldn't you have a mix of gauge and diffeo?
I could. Here it is. That's exactly it. That's exactly it. The point is that you have to add a very specific kind of compensating gauge transformation, which happens to have this form, and that actually is going to be crucial, for example, for Berry phases. Actually, furthermore, for those of you who are sort of more mathematically minded, this will actually turn the representation of diffeomorphisms into a projective representation with a non-zero central extension. So it's really essential for physics. And it's a non-trivial central extension.
Excuse me.
Actually, if you know magnetic translations, this is a generalization of magnetic translations. Yes, you can have as many as you like. Yeah.
It seems to me in physics I would make this deformation in a time-dependent fashion. So why don't you write G as a sort of as the result of a time-dependent deformation?
You should talk to Benoit Estienne. He had this perspective throughout the project, and it's indeed a perspective you can have. Sure, you can think of
it was worked out in detail, then the velocity field that appears in the generation of these diffeomorphisms it plays the role of a vector potential in the dynamics of the electrons.
Sure, fair enough. You will actually see the velocity vector field appearing in the Berry phase.
Yes. And this I don't know what it in physics.
I think
just do a deformation.
No, sure. You will see it in a second in terms of the Hamiltonian. I will actually show what the Hamiltonian does, which is presumably what you would control in an experiment. So indeed, the first thing I should mention is that in symplectic geometry, these deformations are known as quantumorphisms. They actually appear in contact geometry and geometric quantization. But obviously, if you just look at this, this looks very abstract. So I want to give you some intuition on what these deformations do. The first intuition you might ask is, if you're an experimenter and you want to carry out these deformations, you don't know what you're doing in terms of wave functions, but you certainly know what you're doing with the Hamiltonian. So suppose that your Hamiltonian has a Landau kinetic term plus some potential, and conjugate the Hamiltonian with two of these operators. And when you do the commutation, what you find is this kind of transformation of the Hamiltonian. So two things. Notice that you're deforming the potential. You're literally changing the shape of the level curves of the potential. And furthermore, the metric is no longer Euclidean now. There's actually a metric that's induced by this essentially change of coordinates. And so the picture I want you to keep in mind is that these quantumorphisms are deformations that act unitarily and deform both the kinetic term and the potential in the problem. So this was one intuition. The other one is actually pictorial. You can ask, what does this deformation do to the density of a typical wave function? So here's a typical wave function in the lowest Landau level. It's isotropic in symmetric gauge. And if you actually deform it according to this formula, because there's only a phase here, the wave function remains level. If it was level initially, so it had sort of a common maximum value, that value is not going to change, even though you're going to change the actual shape of the wave function. And again, please try to keep this picture in mind, because later, when we turn to potential deformations, we will see a completely different behavior of the wave functions. Okay, but so now that we have this effectively parameter dependence of the system, we can turn to Berry phases and ask what would be the Berry phases resulting from this. And so to actually do the computation, I'm going to begin with the neutral preliminary. Suppose that my wave function is not charged, or there's no magnetic field, and it just transforms in this way under error-preserving maps. And then I'm going to consider some energy eigenstate of some Hamiltonian and ask what happens if I act on that guy with time-dependent adiabatic deformations gt of x. Well, the answer again is given by this general formula for Berry phases I wrote earlier. And what we're going to do now is, again, use the fact that this unitary operator is written here. We're going to use the fact that the scalar product of wave functions is now an integral over the plane, so you can just carry out the computation. And what you find is this seemingly complicated combination of derivatives of psi. But actually, up to half an integration by parts here, this is actually the current density of the wave function, so I'm just going to write this as the current. And the second term here, which is this vector field, that seems complicated. It's the time derivative of the inverse of g evaluated at g, but actually, following Jo's comments, this is actually the fluid velocity of the flow corresponding to g. Actually, technically, it's the fluid velocity of the inverse flow, so I'm going to write it as minus this combination. And in terms of that vector field now, this Berry phase becomes, it's a space-time integral of the pairing between the current one form and the inverse fluid velocity. In fully general terms, this is it. For the neutral case, there's not much more we can say unless I actually tell you what specific kinds of deformations I want to consider. But of course, what we're really interested in is the charged case. And so, if you want to compute the charged version of this Berry phase, you can actually start from the definition of quantumorphisms that I gave earlier. You can carry out the analog of this computation, take care of the fact that it's now a projective representation, so there's an extra contribution. We do that in the paper. I'm not going to do it here. Here instead, I just want to give you a heuristic intuition, really, for what the result has to be. So the first thing is that the Berry phase has to be gauge invariant, that's for sure. And this is not gauge invariant because of this current. So a minimal fix of this is to just replace the current here by the gauge invariant current, where this extra term comes from covariant derivatives. And with that minimal fix, this is actually a gauge invariant Berry phase. And you might think that's the end of the story. It's gauge invariant, so that's it. But actually, that would be forgetting a key fact. Suppose that you have a Gaussian wave function with zero current, but it's in a plane with a magnetic field. When you apply time-dependent translations to a wave function, and it encloses some area in the plane, of course it has to pick up an Aharonov-Bohm phase. And this is not appearing here. So when you actually do the computation, what you find is that there is indeed an Aharonov-Bohm term, which happens to be of this form. You can see that it's a holonomy of A, weighed by the local density of the wave function. And that turns out to be it. This is indeed completely gauge invariant with two separately gauge invariant terms, a current term and an AB phase. Now, we have this neat...
What was that integral?
Which one?
The integral, conta integral over which conta?
So I fix x, I choose a point x in the plane. At every x, I act with the time-dependent differential gt of x, and I integrate over a path gt of x. Keep in mind, I'm assuming my path of diffeomorphisms is closed.
That's the gauge transformation induced by the diffeomorphism, right?
Yes, it comes indeed from the compensating gauge transformation. Yes, that's the key. That's also how you see that in the neutral case, where I had no compensating gauge transformation, I only had this term. Yes, yeah.
What is psi?
A wave function, an eigenstate.
A wave function. What does it describe? If it describes a state of electrons, it will also depend on time.
I'm assuming I'm considering the ground state of some Hamiltonian. Why would it depend on time? It's a station.
Then you have to, so this is why you only look at adiabatic.
Yeah, absolutely. This is adiabatic throughout. I'm in the ground state all the time, even when I change things in a time-dependent manner. I like dynamics too, but that's for another talk. But then, indeed, you can also consider dynamics, but it's a completely different question. No, the adiabatic assumption is crucial in obviously simplifying the problem. So, this is the situation that we have. It's a general formula for these Berry phases, and I really want to stress at this point, this is a formula that I applied here to a one-body wave function, But because this is a unitary operator, if you have an n-body wave function, you can just take the n-fold tensor product of this unitary operator, and you have an action of quantumorphisms on any n-body wave function. And this is true regardless of interactions. If you like Laughlin, apply this to Laughlin, you can do it. Or if you like free electrons, apply it to free electrons. So what I'm going to do now is actually apply this very phase to specific quantum Hall droplets. And for simplicity, I'm going to assume that my reference state is an isotropic quantum Hall droplet. So it looks like a disk. And the two pieces of data that I need to describe the Berry phase are the density and the current. So I'm going to describe them in terms of polar coordinates, r and phi, in terms of which the density takes typically this characteristic form. It's roughly constant in the bulk and then drops to 0 at the edge. So intuitively, I'm going to think of the density as a bulk quantity. And as for the current, it is non-zero in the bulk due to the Hall law, but actually in the limit of very strong magnetic fields, there's actually a noticeable bump of the edge here, of the current on the edge here. So I'm going to think of the current as an edge contribution. So it's really localized here on the red region. And so the question is, what happens if I take these pieces of data, the density and the current, and just decide to write the Berry phase before in terms of polar coordinates? And what you find is this, in principle explicit, but in practice slightly ugly formula. Notice, by the way, that there's a length scale here that appears. That's the magnetic length for those of you who know what it is. If you don't know for now, don't worry. Just think of it as the characteristic length scale of the problem. I will actually write it down explicitly in a few slides when I talk about potential deformations. Yes, Paul?
There is no current in the ground state.
There is, on the edge. Here it is. Take a finite droplet and you find this current.
In the ground state, you can excite current, but then it's a wave propagate. You don't excite, no propagation.
You find it. Keep in mind, first keep in mind that there's a confining potential. So the Hall law has to, even in the bulk, forget the edge, even in the bulk, there has to be a current because of the Hall law.
If there is a confining potential, that means that there is a field applied. That's right, but then diffeomorphisms will be destroyed by this potential.
I mean, I just showed you they can act even with the potential.
Then you have to transform potential as well.
I am transforming it. We can talk later if you want. But like this plot explicitly comes from a, you do the one-body current computation for a state in the lowest Landau level. For free electrons that you sum over the occupied states from 0 to capital N, say, and you find this plot. That's an explicit non-zero.
There is a potential, sure. I thought you were doing without potential.
Yeah, no. There is a confining potential. And crucially, by the way, if you take the Laughlin state, for example, you typically don't assume there's a potential, but you would still see this bump of the current on the edge, even statically.
Sorry, I have a more basic question about notation. Oh, sorry.
Sorry, go ahead.
So those superscripts phi and r
Components.
But G bar, G dot is a vector field, so it has a component, but just GR or G.
Yes. So I'm mapping. I have my coordinates r phi, and I'm mapping them on some function gr of r and phi, g phi of r and phi.
Thank you.
That's it. I chose polar coordinates and wrote everything.
But it's good. Just what is the notation?
Yeah, just that. We can talk later about the current.
There is no current in the ground state, but it's okay. Let's go.
Okay, let's talk.
Something else, but it's okay.
Something related to Paul's question. What is actually a Hall droplet here? Is it to take an infinitely extended lowest Landau level and you truncate it, or is it the ground state in a potential?
It's a ground state in a potential. So if you want to think in terms of free electrons in an isotropic potential, so you can label the states by their angular momentum m, you have the one-body energy Em, you have m here, and then your spectrum is going to be something like this.
It's absolutely.
This, and then I'm just saying, okay, I'm filling my states up to this Fermi energy. This current here, and by the way, the density as well, they're obtained for free. The way I actually plotted them here is for free electrons, where I'm just summing over densities of one-body wave functions and currents of one-body wave functions in this many-body ground state. That's it. Yeah, so It's actually, like, the computation is fairly basic. That's actually the easiest part of the project. The hard part was to compute the Berry phase. Okay, so as I said, this is in principle an explicit formula, but in practice I dare you to use it. So what we did was to apply it to edge deformations, which I mentioned earlier. So you may recall, those are one deformations of the circle compensated by this radial rescaling, and they're smooth everywhere. And so just take these guys, use this convention that I wrote here, plug them back here. What happens is that you find, sort of nicely I think, you find this actually one-dimensional Berry phase, which we found earlier, so this two-dimensional integral of g dot over g prime, multiplied by an overall coefficient, which in this case happens to be this integral of the current and the density. And again, I stress that the current integral, actually the current itself, and the density contribution are separately gauge invariant. The density contribution is an Aharonov-Bohm phase, and the current is just gauge invariant by construction. And so now, yes?
Just a stupid question. In this setup, could you have guessed that you would get something proportional? Like, is there, I don't know, it needs to be some, whatever, cocycle or something. Is there some uniqueness, right? Because now you're saying it's basically Berry's phase, or a cocycle for diffeomorphisms of the circle. Then, of course, the coefficient one needs to compute.
Yes.
But, like, is this an
Right, so when I, indeed, you know, I've worked on circle diffeomorphisms for a while, and I was expecting this to come out. And you know that this is the only thing that can come out because, well, it's a symplectic flux on the quadrant orbit of dFs1, and you know that that's the only thing that can happen. So you knew that would happen. Actually, when I started this, I was hoping to see the central charge contribution as well. But actually, when you look at the group operation here, there's no, so there is a central extension in the area preserving diffeomorphism group, but these particular diffeomorphisms have no central extension. And so there's no central charge here, which is exactly why I move on to other kinds of deformations in the next part. Now, yes?
I remember vaguely, but this combination G dot over G prime, written as a field binds, is the coupling of chiral fermions to the gravity. Is it
Yes, it's in Anton's work from the end of the 80s, it's essentially the two-dimensional gravity action, I believe, right?
That's the Maurer-Cartan form on the diffeomorphism group, right?
Yes, exactly. And also, by the way, nowadays there's people actually working on boundary actions in three-dimensional quantum gravity. These kinds of things appear all the time. That's actually how I came into this. I used to do 3D gravity, and actually I realized this appears in many other contexts. So, thanks for the questions. So now, I mentioned that both of these terms are separately gauge invariant, the currents and the density. So suppose that in some way you decide to neglect the bulk contribution, which is the density, the Aharonov-Bohm phase, and just focus on this current integral, and just compute it for typical quantum Hall states. And what you actually find is that in all cases, this happens to be proportional to Hall viscosity. Actually, in this paper, we show that for integer quantum Hall states, it is exactly 2 times Hall viscosity, and for Laughlin states, it is 2 times the filling fraction times Hall viscosity. So, in this case, we have effectively reproduced Hall viscosity from a planar computation, and we've done it in a way that actually embeds it in an infinite dimensional group of deformations. That's why I mentioned earlier that we would have an infinite parameter generalization of Hall viscosity. However, a drawback of this result, as you can see, is that there is no central charge contribution. Even though we're deforming the edge, we don't see any contribution of the fact that there's actually a CFT with a non-zero central charge. Yes, Julia.
Could I compute the Hall viscosity by looking at an effective action and how it depends on the metric on my sample space? Is that how it is computed, or how do you compute it?
Well, the historical computation, as far as I know, is close in spirit to what I did here. It was microscopic in the sense of wave functions. There is, to my knowledge, a whole bunch of papers that actually do it from the effective action in terms of, I think, when Z terms and these kinds of things, when you add when Z terms added to the Chern-Simons action, as far as I know.
In one of my papers, we did exactly this. We integrated out fermions, get effective action to gravity, and read Hall viscosity.
Exactly. That's done in several references, but it's not the approach I'm following here. But you can. Although, as far as I know, there are claims actually in a paper by Kristen Jensen and collaborators, where they actually say that there's no bulk edge correspondence for the Hall viscosity. Whereas here we seem to be getting...
One of the collaborators of that paper.
You were on the paper, sorry. I remember Kristen because I know him from the gravity fair. And so I have no idea why here we seem to be getting it from the edge. It would be interesting to... This is actually a comment that Shinsei Ryu mentioned to me when I told him about this work. Okay, so as I said, fine. Here we don't have a central charge, so let's try to cure this problem. Yes, by the way, yes, sorry.
Why is the problem? We know that all viscosity is not related to central charge.
Sure, I agree. It's fine. It's not meant to be. But you see, I started from this computation without assuming I would get, I anticipated it in the talk, but when I actually started this, I didn't know that I would get whole viscosity. So I was really hoping to get, especially because I'm deforming edge things, and this is the Virasoro part. As you know, it's the thing that's supposed to be a CFT. So I was expecting a central charge, and there is none. And the reason there is none is actually that you have to consider another kind of deformation, which is by deforming potentials only, not the metric.
So sorry, may I ask?
Yes.
If I take Laffin's, well, not Laffin's one, but the lowest Landau level wave function, I can modify it by adding, as we saw in the previous talks, by e to the holomorphic functions, and then I can just plug it in the standard Berry phase formula and think of this as deformation droplet. Will I get the same result? Or
I don't think so, because this is a different kind of deformation. So I mentioned at the start of the talk that you have to be very careful with what you call a deformation. That's actually exactly why I'm showing this, because the results are very different depending on what you want to do. I'm not a specialist of the plasma analogy, but to my knowledge, when you use the plasma analogy, what you're secretly deforming is the magnetic field, not the potential. If you actually deform the potential, in particular, as I will actually argue here, though it would be sort of hidden, you actually get different results than if you use the plasma analogy. At leading order, it doesn't change much, but as soon as you're hunting for subleading effects, that's actually crucial. And so how you decide to deform, are you deforming the metric, the potential, the magnetic field, that's, at leading order it doesn't change much, at subleading order it changes everything. And these are typically fairly sensitive observables. They're not, at leading order they're zero, or this kind of thing, so you have to be very careful. Okay, so indeed, here I'm going to begin by explaining in what sense deforming the potential is completely different from the quantumorphisms I talked about earlier. And then I'm going to spend some time explaining a semi-classical approach that we developed to actually deal with this problem. And this is actually the part that's going to resonate with what Per Musavi is going to talk about. And finally, I'm going to mention an ongoing computation where we're attempting to use these wave functions to extract a central charge contribution from the Berry phase. I should mention, however, that this part will be somewhat inconclusive, so sorry in advance, but still I hope it's interesting to share these ideas with you. Okay, so our setup again is quantum Hall droplets, and we want to understand, so they're electrons are described by this kind of Hamiltonian, possibly with some actual interactions, and we want to understand what do we even mean by deforming the droplet. Well, we've just seen one way, which is quantumorphisms, that consist in deforming both the kinetic term and the potential. But in practice, in a lab, what you would most naturally do is just to deform the electrostatic potential. And that corresponds to deforming the potential here, while actually not touching the Landau term. And so the question then is, what would be the eigenstates of this kind of deformed Hamiltonian? Well, actually in that case, because this guy is anisotropic, and in fact has no symmetries at all, there is really no exact solution to the problem, so you have to resort to some approximations and simplifying assumptions. Here I'm going to make the two following crucial simplifying assumptions. First, I will assume that this potential is monotonous, meaning that if this is my plane where the electrons lie, I'm going to assume that the potential has a global minimum located here, and as soon as you consider a level curve of the potential with higher area than the previous one, the potential is actually higher. So it really grows monotonously away from the minimum, even though the shape is arbitrary. Second assumption, I'm going to assume that the magnetic field is much, much stronger than the effect of the potential, which in practice means that I'm going to work in the lowest Landau level of the problem. So now I have to explain to you a bit what the lowest Landau level is, even though many people here know. So the lowest Landau level, by definition, is the eigenspace of the Landau Hamiltonian with lowest energy. In symmetric gauge, a basis of the LLL is given by these holomorphic wave functions, actually monomials. And what I'm calling Z here is this dimensionless complex coordinate. By the way, I'm using here a length scale, which is actually the magnetic length that I mentioned earlier. And so when you project all the physics in the lowest Landau level, thanks to this projector, you find some peculiar properties, such as the fact that now the projected position coordinates no longer commute. So space has become non-commutative, and the maximum amount of spatial resolution that you have over any state is limited by the magnetic length. And so now the question is, what would be the projected Schrödinger equation for this anisotropic Landau problem with an anisotropic potential? So let's just project the thing. When you project it, the kinetic term becomes constant, so you can plug it back into the energy here. And effectively, you end up having to solve this problem where the potential itself now plays the role of an effective Hamiltonian in this effective phase space spanned by these coordinates x and y. And so the question is, what is the spectrum of this operator PVP? So let's begin by considering the isotropic case. Suppose that V of G bar of x is just a function of the radial coordinate r, so that the eigenstates of this guy have definite angular momentum. Then, in fact, the only thing you can have is that these states are these states with definite angular momentum m. And so if you actually plot them, if these are the level curves of the potential, the kinds of wave functions you're going to find are these kinds of wave functions localized on circles. What is specific about those circles is that really all these wave functions trace equipotentials, so level curves of the potential, with a quantized area, 2 pi m times L squared. Now, that was the simple isotropic case. Suppose that my potential instead is anisotropic. What can I do in that case? Well, actually, most of what's written on this slide remains true. It is still true that this is a phase space. It's still true that the potential is the effective Hamiltonian. And in fact, if my level curves have, say, this shape, it is actually still true that the eigenstates trace equipotentials with this specific value of quantized area. So if you plot them, you'll find this kind of behavior. And so what I'm now going to do is use this insight to develop a semi-classical approximation to actually find the shape of these wave functions. So in other words, what I'm going to do is work in the limit of small magnetic length compared with the length scale of the potential, and I'll work in the limit of very large quantum numbers n. So in other words, I really want to develop a W can be ansatz for these wave functions, which is to say that, so let me explain how you actually make this ansatz. And this, by the way, is crucial because, again, Per Musavi is going to use parts of this ansatz in his talk. So the way to build it is as follows. First, pick an equipotential. So here it is. Now, you cannot quite pick the equipotential at random. You have to do it in such a way that the area it encloses is quantized in this particular way. So you fix the area once and for all. Now, suppose that you measure the area of different neighboring equipotentials. You can think of this area as, because I've assumed that my potential is monotonous, you can think of this area as a radial coordinate. And so there's a canonically conjugate angle coordinate theta. And so in terms of this coordinate theta, I'm now going to write the WKB ansatz as written here. Now, if you just look at this formula, it looks a bit unwieldy, so I want to spend some time explaining what it is. Let's first look at this ket x m theta here. So that's a delta function, wave function, localized at some point in the equipotential. So here, say this is the point here. I don't know if you can actually see the point, but it's localized there. So I pick one such point, and actually I do that for every theta. So instead of picking just one point, I take many of them and I integrate over theta. So that's the first step. Once I've done that, I actually have to weigh this integral, the integrand, first by this phase, e to the im theta, which you can think of as the leading term of the WKB approximation, and then by this function n theta, which allows the wave function to be modulated as a function of theta. Finally, if there were no projector, this would not belong to the lowest Landau level, so I have to end by projecting everything to the LLL, which turns this infinitely localized wave function into a Gaussian of this kind. And so that's it. That's the ansatz you can use by actually plugging this. You can plug this expression into the Schrödinger equation, expand everything in powers of the magnetic length, and find the differential equation for this function n. So I'm not going to do this in detail. I'm actually just going to show you the results in the case of edge-deformed traps. Indeed, recall that these edge deformations are of this form. And suppose that you look at the radial component of this and use that as the argument for the potential. So now you have a potential whose shape is given by this. In that case, it turns out that this coordinate theta is just g of phi, so you have all the data needed to write this explicitly. So do it, plug it in the Schrödinger equation, deduce the differential equation for n, and what you end up finding is certain near Gaussian states that happen to take the form written here. Now, this is fairly explicit, even though it's a bit ugly, so let me again specify a few things. First, notice that I've written the wave function in polar coordinates, so here's the radius, the dimensionless radius z, and here's the angle phi. By the way, this is a wave function in the lowest Landau level, so you can actually write it as holomorphic wave function times e to the minus z squared, but because this result comes from an asymptotic analysis close to the equipotential, the manifest holomorphicity is lost. You don't actually see it. It's there, but you don't see it. Now, a few comments about this. First, notice that here there's a leading term e to the im g of phi That's a remnant of the E to the m theta, and actually that you can think of that as the leading term of the WKB approximation. Secondly, notice that the wave function is indeed a Gaussian of this form. It's localized on an equipotential. And finally, notice that there is indeed a space-dependent modulation. So everything here is a function of phi. And notice the exponent 1/4 that you may be familiar with from WKB. Again, pictures, I think, can explain the...
What is this capital phi of phi?
Very good. So that's a horrible phase that you can compute explicitly, which pair is actually going... I think you're going to show it, right?
Yes.
So you can actually compute it. And it's important for Berry phases, as I will explain. But here, for simplicity, I'm hiding it. Now, again, here's a picture where you can start from an initially isotropic state. And if you deform it, it should be okay. I'll skip the conclusion. So you can deform it, and you can see that as you do this, you get this sort of roller coaster behavior that's completely different from the behavior of quantumorphisms that we found earlier. So this is indeed a completely different kind of deformation than quantumorphisms. And so I'm essentially going to conclude by mentioning essentially what's an outlook, which is how you could hope to use these changes of potentials to actually compute the Berry phase. So again, you would take your potential to be like this, now with a time-dependent deformation, and you would apply this kind of time-dependent deformations to your wave function. So the question is, what's the Berry phase that you find when you do this? So the Berry phase, again, is given by this same formula as before, and all you need to know is what specifically is this parameter-dependent wave function here, which now depends on a parameter, which is a point in a diffs1 group manifold. So it's given by this, and you have to be brave, take the whole thing, including the horrible phase, plug it back here, compute scalar products, and hope for the best. So that's what we started doing. And if you actually focus, for example, on the contribution of the first term, the result is actually quite reassuring. The leading term of WKB actually gives you a one-dimensional Aharonov-Bohm phase, exactly as we found before, weighed by the local area of the wave function. So it's perfect. And furthermore, if you look at this contribution here from the weight of the Gaussian, and you can compute its contribution, you beautifully find this kind of term that looks like a CFT central charge. And so that was the status of this computation about, I guess, 2.5 months ago. And I was very happy because I thought, okay, that's it. Within a month, we'll have CFT Berry phases with the correct central charge. But actually, that was overly optimistic because there's a bunch of other terms hidden, for example, in this phase here. And actually, there's a lot of other things going on. And so in the future, I hope to actually have more to say about this and hopefully some more definite results involving central charges. So given time, I'm actually going to skip the conclusion, just show you the slide of the conclusion. I'll first say thank you. Thanks for your attention. And then if you want to discuss, here are the things we can talk about. Thank you.
Thank you very much. Are there any questions?
So the central charge, would that be just for the lowest Landau level?
Yeah, it would be one.
You know, because if you have several edge channels, then of course the theory is not really conformal because they have different propagation speeds, and it's a little unclear what you mean by the central charge.
The truth is, I'm not actually sure this is a CFT central charge. I think it's actually a gravitational central charge. So the anomalous one that comes from the difference between left and right movers. Right. I'm calling it a CFT central charge, but actually, as you said, I very much look forward to doing the higher Landau level generalization of this. That's absolutely on the table, on the program.
And if I may ask another question, this analysis gives the answer to which physical question?
To me, the general motivation is this. I want to understand in what sense it is true that when you have, in general, a topological insulator, can you prove microscopically, without assuming effective field theory, can you prove, obviously it's not true at the level of a single wave function that it's redundant under diffeomorphisms, but somehow in quantum Hall fluids, there is an emergent gauge symmetry in the bulk, which I would like to find. So I want to understand, by studying the response of these systems to deformations, I want to understand how this emerges. That's the broad motivation. And then the other motivation is actually much more experimental. Nowadays, you can actually make experiments that give you local imaging of wave functions, and you can see, the wave functions I showed with the roller coaster type behavior, you can actually plot that. And you can see nice geometric effects of essentially Kähler geometry in the shape of the wave function. So that's another, if you will, experimental motivation.
Another question.
Many instances about the motivation, and it may be off topic, but sometimes you have a material and nowadays they strain these materials. And it looks to me that you could argue that, okay, what you're studying essentially with this potential deformation, since you have this, I don't know, you change your potential, and then you study it in this well, so you essentially, this would be like studying one, if you think about a tight binding limit of such a material, right, then maybe this would be similar analysis, but I don't know if there's any connection to sort of mechanical strains of material, or mechanical straining materials and this.
Yes, so that's obviously another question that needs to be addressed. I should mention that in the one-dimensional case, at least in one-dimensional conformal field theory, there is some control as to what you can actually do to your sample in a tight binding model to generate these kinds of deformations. Actually, Per Musavi is, I believe, one of these kind of questions. And so my hope is that by sort of harnessing what we know in 1D, we can actually move on to more complex materials and understand what it means, you know, how you can have an emergent notion of diffeomorphism in a material that, say, in a tight binding model. Obviously, it's discrete, so you would have a discrete version of diffeomorphism that actually becomes continuous in the thermodynamic limit, so that obviously needs to be addressed. Yes? Yes.
Just to clarify the issue. So we have a, say, integer countable effect, wave function, many body wave function, or orbitals, whatever, for a circular droplet. That state has a given orbital momentum. Just number.
Angular momentum.
Angular momentum.
Sure.
Now you deform it somehow. You will get a different wave function.
Along the deformation, yes?
After deformation, can you write this wave function? How different it from original wave function?
You mean, wait, are you referring
So
to...
what you wrote is a little bit too abstract, but maybe some...
Wait, are you referring to quantumorphisms or potential deformations? In both cases, in principle, I gave
Whatever. So, some wave function. You draw a picture with curved orbitals,
Yes.
deformed disk.
Yes.
So what is the wave function? Yeah, that's too many notations here, difficult to...
Sorry.
Maybe there is some, just one, maybe there, 1 second, maybe there is some explicit form. Let me ask a question. Suppose, just a question. Suppose you give a shape of this edge, right? So
Yep.
prescribed shape. I give you this shape.
Yep.
From this shape, can you write the orbital?
The shape is G prime.
The shape,
That's
what does
different.
it mean, the shape? Shape is a curve, right? Two dimension. It's a curve on a plane.
Yeah, sure. Oh, it's a good question. And so first, it's a pretty natural question because I don't expect the audience to understand this kind of formula within 2 minutes of just seeing it. It took us months to sort of get a grasp. But actually, it's a very important question. So if I show you this droplet.
Yeah. So this curve is given.
Yeah. You give me the curve, and I'm going to describe it as follows. I'm going to say this set of points here, the edge, is a set of points where r squared over 2 is equal to, now let me not mix this up, it's L squared times number of particles times G prime phi. L is the magnetic length, and number of electrons, G prime of phi is the function I'm using as a parameter. So effectively, G prime is the shape. That's what I meant. That's the, wait, yes, this is it. That's the shape.
Okay.
And so you use that shape, you plug it here, there you have it.
There is too many.
Right.
There is another letter there. Capital Phi, I guess.
Yes, so capital Phi, so I'm going to try from memory. Capital Phi, I'm going to try from memory, and I'm going to stop here. Because it's some function of G. It's something like 1/2 G of phi minus phi plus the energy correction, which you can compute. So the energy correction is an integral of G prime prime squared over G prime squared d phi with some coefficient here that you can compute from the potential, plus a bunch of other things, all of which depend explicitly on G. In the paper, we actually give them.
Maybe you know, normally that kind of object formed expressed through Schwarz function, which is defined by the curve. Maybe you know that formula. It will be easier to
actually hope so. Actually, that's one of the things I wanted to talk with you about because I don't know that.
So it's not. It's maybe the same or
might be the same, but I don't know. Note that in the paper, precisely because of this kind of confusion, initially Sorry, we have to stop? Okay.
Okay, I'm sorry, we must leave this to private discussion. So let's thank Lagoye once again.